You guys ready to, get a little introduction to the lab that to do the more accurate way?
Yeah.
Okay. Well, it's not. It's a bit more precise. We're only going to introduce you a little bit. If you go on to the one series, they're going to actually do it with calculus. You can even get even better. But here's the rule: you can kind of already see kind of evolving from right here between this and this. You can kind of see where we're going to go with this. So let's now do the now and I'll let you know which one method you should use, whether this one before the sig fig method or the error analysis method. Let's be a bit more sophisticated. I can't spell sophisticated apparently. Sorry. So just I want to let you guys know right off the bat that I have dyslexia, so I will flip things around. If there's an inconsistency with what I say and what I write or type, please bring it to my attention. It's gonna happen. Happens it's just to let you know right off the bat. I'll try my best to not make those kinds of mistakes and to catch them, but some will slip through. Just FYI. In our it usually comes up like a long word like that. Let's double check. For the lab. I'm just pulling it up on my other screen here so I can look at it and basically correspond to it. So let's say we go back to measuring a length again. I'm stealing from the lab. Oops. So we have an experimenter measure the length of 27.4 using a meter stick. Centimeters using a meter stick. They estimate that the last digit has an absolute error of zero point 0.1 centimeters, which is like the smallest tick mark on here. So let me just pull up a ruler here, or a meter stick. Let me just get a little picture of that, because trying to draw it is going to be a pain in the butt. Image. Go away. Okay. So this is what's going on. So you can see that these are centimeters here, and here these are millimeters. Right? So you could say that, the smallest tick mark is, it could be between, 1 millimeter one way and 1 millimeter the other way. So the big tick marks are centimeters. And the small tick marks are 0.1 centimeters or 1 millimeter. On a meter stick. Standard meter stick. Now we're going to simulate more accurate ones using vernier calipers. And I was debating on actually having you guys buy like a lab kit with vernier calipers to have you guys practice, but I couldn't find any lab kits that could, be cheap and easily accessible. There are some cheap vernier calipers if you want to play with them, but we're going to play with virtual ones. They're going to be more accurate than this. All right. So that's why we say it's going to be, the accuracy is in 1 millimeter for a metric stick meter. Now the percent error, this is the absolute error, this is the percent error. Let me zoom in a little bit. Hold on, let me move it over here. You guys still see it, or did it disappear? Disappeared. Okay, let's hold on. Let me fix this. You guys see it again?
Yep.
Okay. Hold on. Where'd it go? One sec. I misplaced my Apple Pencil somewhere. Where'd it go? Drop it? Oh, there it is. Cool. All right. So this is my absolute error. And this on the other side is my relative error or percent error. So you get the relative error by taking 0.01 centimeters and then dividing by 27.4 centimeters. And you get 0.004 rounded to 1 sig fig. And you can write that as equal to 0.4%. Percent meaning per 100, so you multiply by 100. By the way, you can write this as either like this or like this on your labs. I'll understand both. Note that the percent error doesn't have units. Where the absolute error does. Okay. Questions so far? So far, so straightforward. Let me just actually make it abundantly clear that we're on a new topic right now. This is a new topic. So let's go ahead and say we had an angle of stealing this from your lab. If you want to follow along, actually look at your lab, right? The first thing, download the PDF from the lab manual that's posted there. So we got 93 is measured with a protractor. Now, protractor usually has plus or minus 1 degree, sometimes half a degree, but let's go ahead and say it's 1 degree. So we have 93.1. If you divide 1 divided by 93, you get 1 point with some other stuff. Now we have percent error should only be 1 digit unless it's 1. And then you have 2 digits. Here's the last one here. A length of 27.43 is measured with the ruler. The absolute error in the last digit is half a millimeter, or because let's say you could actually say, I can get really close here, and I can say like, well, I can say whether it's close to the middle or closer to 1/2. That's how you can estimate like half of a tick mark sometimes. Sometimes you can, sometimes you can't. It's a judgment call on your part on whether you can say, whether I can say, I'm about halfway between tick marks. By the way, on a vernier caliper, you cannot do half tick marks, but there are sophisticated methods that I'll show you to get more accurate. So like, yeah. So the rules for writing absolute and relative errors. The absolute error must be expressed as 1 sig fig. And there should be the same number of significant figures after the decimal point in both the measurement and the absolute error. So basically, these should line up here. Like, if you had more digits after here, they're meaningless. Any digits you have after here mean absolutely nothing because they're overwhelmed by your absolute error. So usually for percent error, is given with 1 significant figure unless the percent starts with a digit 1, in case 2 sig figs are used. All right. Everyone follow along with the rules of just writing them first. We haven't done any propagation yet. We've just talked about how to write the errors.
Yes.
Cool. How about everyone else? Hold on, let me get my fan. It's a little warm with all the lights under here. That fan isn't too noisy, right?
Oh, that's good.
Okay, cool. Yeah. Okay, let's talk about how we would propagate them. So, the primary purpose for the study of errors and the propagation of errors is to find the error in the result from a calculated measurement if we already know the errors in the measurements. This is kind of what we did with the sig fig stuff, but we'll be a little bit more careful and more accurate with it. Because, like, before, the error could have been larger, could have been smaller, but here these are gonna be upper bounds on the error. It could be better than this, but it's gonna be at least this big. Let's see. Do I have my book on uncertainty easily reachable? Let's see. Where is it? There is a book on uncertainty which I have lying around somewhere. I just don't know where I put it. I thought I had it here. Oh, here it is. Hold on, let me go ahead and reach for it. On my, I got a whole bunch of textbooks right here. I just need to grab it. If you want a more sophisticated introduction to error analysis, here's a book right here. It famously has someone who had, problems propagating their error. And so you have can you guys see that? This photo here? Let me just stop the sharing so you look more closely on mine.
Is that a train
It is a train
coming out of a window?
going right through the train station. Yeah, this is someone who didn't propagate their error correctly. Or, error analysis can be, all it had is like an error in the last digit. It was just a little bit for the whole train trip. But yeah, this book right here. It's if you want a more detailed analysis, you go ahead and check this book out. But here we're going to just do the basics. All right. So here is the 2 rules that we'll be using in your lab today, and for like more general. So when you add or subtract items, the maximum absolute error is, and the result is the sum of the absolute errors in separate terms, taking all positive values. So basically, you only add the errors. You only get more error. You never have errors subtract. And you multiply or divide, you add the maximum percent error to each. If a factor is raised to an exponent, you multiply that by exponent multiplied times the magnitude of the exponent of the factor. All right. So these are the 2 rules that we'll be using. If you want more sophisticated measurements, well, this book, or there's a summary on Wikipedia for propagation of errors. You need calculus, though, unfortunately, to really dive into it. All we're doing here is just doing kind of the basic ones. Here. All right. So if you're kind of curious about how to get the more sophisticated ones, it has propagation of certainty, and just skip to the end of it for the whole table for example formula. Oops. Oh, do you guys see this shared here or no? No, it's not sharing, is it? Is it sharing? You guys see it?
What are we supposed to be looking at?
Oh, just the propagation of errors. You guys see it?
Yeah.
Okay. It just isn't highlighting in green, so I wasn't sure whether you guys can see it or not. Usually I can see it highlighted in green, but not right now. Okay. So here's a couple examples before I let you guys take a break. So when you add, let's see these measurements right here, you add the absolute errors here. So we have 78.2 plus or minus 0.1, 14.4 plus or minus 0.3, and 183.4 plus or minus 0.2. Because before, we would just say that these all had uncertainty in the last digit, and you would say plus or minus 0.1. That's an underestimate. It's actually 0.6 because these all have their own errors that are bigger than that. And if you subtract, you still add the errors. This is because this could have taken off a lot more or less with this meters right here. That's why you have to add the errors. This makes sense why you have to add the errors even when you subtract. So the errors never get smaller. When you propagate errors, the only way errors can get smaller is by two ways. One, get better measurements. One, take measurements with less uncertainty. Or two, do analysis that propagates less error. By being clever with the steps you take. I'll show you about being what I mean by being clever. Because sometimes like there's a way to get like the standard way that you might do it has some error, but you can be clever and get smaller errors without changing the measurements at all, just on how you propagate the errors. All right, questions on this so far?
Not from me.
How about everyone else?
All good so far.
If you have questions, you can also privately chat me too. So here's one with multiplication and division, with a couple of them having exponents. So we have some constant b is 74.7 plus or minus a half a centimeter. R, which is 0.92 plus or minus 0.03 centimeters. And m is 402 plus or minus 2 centimeters. The quantity q is obtained from the formula q equals 2 are b squared over m. Find q and the maximum error in q. So we calculate q first by plugging in, the measurements we have for 2.92, 74.7, and 402 to give you 26 centimeters squared. The percent error in q, though, is so 2 doesn't give you any percent error because it's an absolute number. Constants do not change your percent error. Constants do change your absolute error, though. So let's say we had like an object and we divide it by 2. The absolute error goes down by a factor of 2, but the relative error stays the same. That makes sense? Hopefully you remember that because that's important on the lab you're going to do. All right. Okay. So there's actually 2 factors of b here because it's b squared. So we actually 2 times the percent error in b plus the percent error in m. Even though we're dividing by it, we still add the percent error. And so we get 3 plus 2 times 0.7 plus 0.5 to give you 5%. So we have 26 centimeters squared plus or minus 5%. And I would say you should also have the absolute error as well. So I'll add that in right now. Plus or minus, you get back 26 times 0.5, which gives you 1 square centimeter. Okay. Any questions? We're going to do a couple more after the break. But I think now is a good time to take a break.
Did
All
you
right.
say 26 times 0.5?
Sorry, what?
Right now, when you were calculating Q equals 26 centimeters squared plus or minus 5%, you said that it was 26 times 0.5, correct?
Yeah, I get this back right here. So I'll show you here. It was 26 centimeters squared times 0.05 gave me, it was 1.3 centimeters squared, but then I rounded to 1 sig fig.
That's what I heard. I thought you said 0. Not 0. I got you.
I might have misspoke. Thanks for clarifying. Any other questions before we take our break?
Just to be clear, you multiplied it by 0.05 because of the percent error, right?
Mm-hmm.
Well,
Yes.
wait.
To get the absolute error back, yes, Delana. Exactly right. Other questions? Okay, then let's come back at 11:12, and I'll see you guys then.